Next section, we're talking about continuity, which if you guys follow along in your book, like I'm sure you do, I'm not really going to do this the way the book does it, but I think what I will do will make a little bit more sense. They try to do a very formal approach, and you're not prepared.
I don't know where it went. I always have. No, I didn't even use a pencil first time, so I don't know how.
Do you have an extra
No, somebody stole mine. Who did I loan it to? That's a good question. I don't remember who I gave it to. All right. So, we've talked about continuity in like college algebra, and we said that a graph is continuous as long as you don't have a break in that graph. So anywhere we have a break in our graph, we know it's not continuous. So if you have to pick up your pencil when you're drawing it, then that's a place where it's not continuous. We are going to kind of narrow down that definition and make it a little more precise now than just saying it's where we pick up our pencil when we're drawing it. So we have been able to find a lot of limits so far, but the issues, the places where sometimes we can't, it all comes down to this idea of continuity. When we have a limit, that's because our graph was continuous. The places where our limit was sometimes something weird, that was because we had a function that was not continuous. So for us, if you're looking at the definition of continuity, there are three things that have to happen for a function to be continuous. It has to be defined. So that means it has to be in the domain. So think about things that are not in the domain, like if you have a square root, we know you can't have a negative under there. If we have a fraction, we know the bottom can't be 0. So those numbers that make the bottom of a fraction 0 or make the inside of a square root negative, those are places where the graph's not continuous because it's not defined there. Second thing, the limit has to exist. Okay, so we think sometimes like a piecewise function, we might have a break in our graph. So the function's defined, but the limit doesn't exist because it jumps from one piece to the next. So to be continuous, the function has to be defined, the limit has to exist, and the third is those two things have to be equal. So I would highlight this box or star it something, because from now on, anytime I ask you where it's continuous, you're going to have to tell me if it's not using one of these three rules. So I will say, which rule of continuity did it break? And you have to be able to tell me that. So the function has to exist, the limit has to exist, and the two have to be equal. Anywhere where this doesn't happen is what's called a discontinuity. So, if I gave you this graph, and I asked where it was continuous, where is it discontinuous, and why? And that's typically what I'm going to ask. Instead of saying where is it continuous, I'm going to say where is it not continuous. So you could probably, just from your college algebra knowledge, tell me where is this not going to be continuous? At 3. Where else? At 5. And at 1. Those are the three places that if I'm tracing this, I have to stop and pick up my pencil and jump over those or jump to the next step. Okay, so the reason has to be one of those three rules. So at 3, is the function defined at 3? Do I have a closed circle somewhere at 3? Yes, the function is defined. The function exists. Does the limit exist? Right, as I'm coming in from the left and right, I get two different numbers. So the reason it is not continuous at 3 is the limit does not exist. Right, at 5, does the function exist? Do I have a closed circle? Yeah. We have a closed circle up here. So the limit exists, or sorry, the function exists. Does the limit exist as I'm coming in from the left and the right? Do those match up? Yes, so the function exists, the limit exists. Are those two equal? No. So you could say the limit does not equal the function. You can give me like actual notation, f of 5 is not the same as limit as x approaches 5. I don't really care how precise you are in your explanation, you're just telling me one of the three rules. So it has a limit, the function exists, but those two are different numbers, so that's why it's not continuous. All right, at 1, does the function exist? No, there is no closed circle here, so the function does not exist, or f of 1 does not exist. So this illustrated the 3 rules and how each of those 3 rules might be violated. Is that okay? All right, so now we're just going to practice this. I'm trying to give us a variety of problems today, and what we're going to do is kind of find some patterns. So things that would be concerning when you have functions, we know like polynomials. Will we ever have a problem with a polynomial? No, they're just a nice smooth graph. What about piecewise functions? Yes, when you jump from one piece to the next, we might have a problem. Rational functions, when you have fractions, we might have a problem because we have vertical asymptotes and things that show up on those. So we're looking at those different types of functions, mainly fractions and piecewise. Those are going to be the big ones where we're going to have continuity issues. So if I gave us this problem, the graph of f of x equals 1 over x minus 2. Graph it on your calculator real quick. And we should get a graph that looks a lot like this. We have a vertical asymptote at 2, y. 2 makes the denominator 0, so we get a vertical asymptote. Put the x minus 2 in parentheses when you plug it in your calculator, so 1 over parentheses x minus 2. They're bigger?
I think mine's like in a scatter plot,
Okay.
so.
So you can turn that off just by having it in there. And then if it goes in 6, it'll be 7 like that.
Okay, thank you. You're welcome.
Okay, so this is discontinuous where? At x equals 2. Right, and we could see that from the original. And this one actually violates several rules. Is the function defined at 2? No. So my reason I could say the function does not exist. Does the limit exist at 2 either? No, because the left and right don't match. So you could tell me the function doesn't exist, or you could tell me the limit does not exist for your justification. You wouldn't necessarily have to give both, but you would have to use one of those two if you're explaining why. All right, next one. If I look at a piecewise, we get 1 if x is greater than or equal to 0. So if you put in 0, you get out 1. If you put in 1, you get 1, 2, 1. That's just a horizontal line this way. Negative 1 if x is less than 0. So if you put in 0, negative 1, you would get open. Negative 1, negative 1, negative 2, negative 1. So where is this discontinuous? At 0. And And you notice that's because it was where we jumped from one step of the piecewise to the next. Okay, if I asked you why, is the function defined at 0? We have a closed circle. Does the limit exist? No, so you could say the limit does not exist, or the limit as x approaches 0 does not exist. Either is fine. Alright, let's look at some more. I think I put a blank slide after this one so you had a little extra room to work out because I put 4 examples on one slide here. So A, can you guys just look at this and tell me where it's probably not continuous? Why? Okay, so we could look at a graph if we wanted, or we could recognize, hey, this is a fraction. I know the bottom can't be 0, so it would have to be discontinuous at x equals 2. And my reason is that f of 2 does not exist, or the function does not exist at 2. You cannot plug a 2 into that equation. Does everybody feel like you could look at that and identify it without me drawing the graph out? So if you have a fraction, anything that makes the bottom 0 is an automatic discontinuity. All right, B. Can you look at that and tell me where we will probably have a discontinuity? At 0, because that's the breaking point. Now, it's not a guaranteed, because sometimes we have piecewise functions where the two pieces match up and touch. So you do have to be a little bit careful. To figure it out, you could either draw a graph, so 1 over x squared, 1 over 1 squared is 1, put in 2, you get 1/4, put in 1/2, you would get 4. You get the same thing with the negatives. Could use your calculator to kind of double check that graph. This was also one of our parent functions in college algebra, so we've seen it before. So that's the first piece, and we can't plug 0 into that anyway. We're getting a vertical asymptote at 0. How do you graph 1 if x equals 0? It's only at that one point though. When x is 0, we get out 1, so it's just a dot. So we could see this is definitely discontinuous at 0. Is the function defined at 0? Yes, because of this piece. Does the limit exist at 0? Yeah, both the left and right are going to infinity. So what's my reason? The limit does not equal the function. Okay, C. This is kind of a combination. You know, it's the same fraction as I had in A, but what did I do? Yeah, I have a second piece defined. Alright, so let's see what this looks like. If you graph this fraction, x squared minus x minus 2 over x minus 2. What do you get? Yeah, it looks like a line. If we had factored the top, what happens to the x minus 2's? Those cancel and just give us x plus 1. So what this is a line, y-intercept of 1, slope of 1, but it has a hole in it at 2 because x couldn't equal 2. Okay, and then the second piece of the piecewise is 1 when x equals 2. So does this still have a discontinuity? So So still discontinuous at 2. Is the function defined at 2 now? Yes. Does the limit exist at 2? Yes. So my reason is that the limit is not equal to the function. Last one. What is that double barred x we saw it a few days ago? Step function, the greatest integer function. Remember it looked something like this. So is this one continuous? No. It's discontinuous at a lot of places. -1, 0, 1, 2. So this is discontinuous at every integer. Is the function defined at the integers? Yes, because we have a closed circle. Does the limit exist at the integers? No. So we're kind of getting an idea of what makes things discontinuous. Now, we need to talk about the second component today is we can classify there are different types of discontinuities. The one that we saw in C and also A, if we had drawn this graph on A, it would have been the same as the graph on C, just without that point. So these are what are called removable discontinuities, because they're almost continuous. We just have one point that's been taken out. And if I could fill in that point, then it would fix it, and it would be continuous. So A and C, those are the removable. If it can be fixed by just a single point, then it would work. If I looked at C, I could fix this discontinuity if on this step, instead of saying it's 1 when x equals 2, if I said it was 3 when x equals 2. That would have filled in the circle on the line, and then it would have been continuous. So if it's just that point, that's removable. The removable happens when you have a fraction and something cancels out, because that puts open circles on our graph. Remember those holes in our graph from college algebra. So anytime something cancels out the top and bottom, that will be a removable. The other potential situation for a removable is a piecewise function, where one of your pieces is something like x if x does not equal 4, and the other piece is something else at that single point. So when your conditions are not equal and equal, that is possibly a removable discontinuity. The second type, infinite. Those are when we have vertical asymptotes. So when our limit is going to positive or negative infinity, that's an infinite discontinuity. The final type is a jump discontinuity. That typically happens on the piecewise functions, where one piece is a greater than and the other piece is a less than. That's when you are physically just picking up your pencil and jumping to the next type. Okay, so 3 different types of discontinuity: removable, infinite, and jump. Any questions about those? It is also possible to be continuous from the left or the right only. You know, if, let's say, if I had a function that looked like this. Okay. Is this one continuous at 0? No. But I could say it's continuous from the right. The function exists at 0. As I'm coming in from the right, the limit exists, it's right here, And from the right, does the limit equal the function? Yes. From the left, we could still say the function exists and the limit exists, but as I'm coming in from the left, my limit is a -1, and so it's not equal to the same thing. So at some point, we might talk about being continuous from one side, and that is an option. All right, we're just going to practice some more functions now. All right, what's this look like? Yeah, this is just polynomial, right? So do I have anything to worry about? No, this is polynomial. There are no breaks in that graph, so it's continuous on negative infinity to positive infinity. No issues with that one. All right, if I give you a fraction, where have I told you you have to watch when you have a fraction? The denominator. So all I really need to do is figure out what makes this denominator 0. So you get 3/5. So it is discontinuous at 3/5. If I want to tell where it was continuous, it's continuous everywhere else. From negative infinity to 3/5 union 3/5 to infinity. So the only break we have in that graph is what makes the denominator 0. Um, 5/3. Yeah, I meant 5/3. Just making sure you were awake. All right, better now? What would be the reasoning on this one? Why is it not continuous there? The function does not exist. Okay. What type would it be? If you have something, when we go to graph it, we would get what? An infinite, because we would have a vertical asymptote there. And so that would be an infinite discontinuity. All right, let's look at another one. Sorry, I don't know why that one typed weird, but this is just another fraction. So in a fraction, what do we have to worry about? When the denominator is equal to 0. Does that factor nicely? No. How can you solve it if it doesn't factor nicely? Quadratic. X equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So when I do that, I get a negative under my radical. What does that tell me? What kind of number is it if you have a negative under the radical? Imaginary. Do I have to worry about imaginary? No, when I'm graphing that, I don't graph the imaginary numbers. So that means the only thing that makes this equal 0 is an imaginary number. So it's continuous everywhere. One more like this. If I have x minus 1 over x squared minus 4, what do we have to do? So this graph is discontinuous where? If we get two vertical asymptotes on that graph. So we'll have breaks at both of them. Any questions there? I want to look at this one. So we are going to find the discontinuities and decide if it is removable. All right, so in a fraction, what should be the first thing we do? After the bottom. So multiply 2 and add to negative 3. The x minus 1, x minus 2. So what I see right now is the x minus 2's drop. All right, it's still discontinuous at two places. What would they be? And 2, because it's discontinuous for each thing that makes the bottom 0. In a fraction, if it doesn't cancel out, that means we're going to get a vertical asymptote there. So what kind of discontinuity is it? If it does cancel, that means when I graph it, I get a hole in my graph. So that is a removable. So when something cancels, we have a removable discontinuity. We're going to stop on this noting up for a minute, and I have a handout with just extra examples I want to walk through together. Look at this handout together. All right, so the first problems, we are just deciding the intervals where it is continuous. Right, so when I look at this, without even looking at the graph, can everybody identify where we might have a problem? One is potentially the problem, because that's where we jump. Okay, so without graphing, really the easy way to see is to see if these pieces would match up. Okay, we know that sometimes when we're graphing those piecewise, they match up. So if I put in a 1, this one gives me a 0. If I put in a 1 to this one, we get 1.5. So do those two match up? No, so it is discontinuous at 1. The question said, tell me where it is continuous. So it's everywhere except 1. So negative infinity to 1, union 1 to infinity. So since those two pieces do not match up, it's discontinuous there. All right, the second one. We have a fraction. So in fractions, we know our concerning piece is what makes the bottom 0. Is the bottom ever 0 here? So where is it continuous? If I'm looking at this one, what is the problem here? The fraction. Let's factor the denominator. So we can take out an x. X minus 3. So where is this thing discontinuous? So it's continuous everywhere else. Negative infinity to 0, between 0 and 3, and bigger than 3. Okay, where is this one possibly a problem? At 1. To see if it is, we need to verify if the pieces match up. So we know the second piece is going to give us a -2. Plug a 1 into the first piece. So we get -1 plus 4 minus 1, so we get, so it would be -2 plus 4, which is 2. So do the pieces match up? No. So it's discontinuous at 1. So that means it's continuous everywhere else. All right. We could certainly have drawn graphs on all of those, but I'm just trying to focus on the pieces in the equation that make it not work. Are we okay with all of those? All right. So next ones. We are still looking at continuity, but we're also going to classify any discontinuity. What are the 3 types? Jump, removable, and infinite. Okay. On these fractions, we need to start by factoring. Denominator, we can't do anything. The numerator, x squared minus 4, we factor into x plus 2, x minus 2. Anytime something cancels, we have a discontinuity at, what makes x plus 2 equal 0? So discontinuity at -2. If it cancels out, what kind is it? Removable. Because when it cancels, that puts a hole on our graph. So we can fix it just by filling in that open circle. This one. Where are we going to have a discontinuity most likely? At 1. Alright, verify it. The first one gives us 0. If I put 1 into the second one, I get 1 out. So they definitely don't match, so it is discontinuous. With these piecewise, it will either be a jump or a removable. Removable happens when your conditions are equal and not equal. When we have inequalities, that means we're up on one piece and then we jump down to the next. So that's what would create a jump discontinuity. So which type would this be? Okay, let's graph it then. 0 if x is less than or equal to 1. So I put in 1, I get 0, 0, 0, -1, 0. Okay, if I put in a 1 for this, I get 1, that's open. Put in a 2, I get -1 plus 3/2, which is a half. Okay. Removable requires 2 connected pieces with just an open circle. Did that happen? No. And I knew it wouldn't happen because my conditions weren't equal and not equal. Infinite requires vertical asymptotes. Did that happen here? No. What happened? We were on this piece for less than, and then we jumped to a new piece for greater than. So this is a jump discontinuity.
So which one has to be for like the greater than or equal to, or one's like equal to and one's not equal to? Is that
Equal and not equal would be removable. So what should I do on this one? So the bottom, multiply to negative 3 and add to positive 2 will be plus 3 and minus 2. Does anything cancel? We still have two discontinuities. And it's what makes the bottom 0. So that would be at x equals negative 3 and x equals positive 1. Since neither of those cancel, that means what's happening on our graph at both? Vertical asymptote. So what kind of discontinuity is it? Infinite for both. We're going to stop when we get to number 10. First of all, we have to look, where do we think we have a discontinuity? Negative 2. Verify that it is in fact a discontinuity and that these pieces don't match up. Okay, the second piece is definitely giving me 0. If I plug in negative 2 into the first, we get 4 minus 12 plus 9, which is 1. So they don't match up, so it is in fact a discontinuity. Now what this is saying is we're on the top parabola all the time, except the one point when x is negative 2. And there I gave you a different point. So if you were to graph this, okay, it's just a parabola that has an open circle at one point. So I'm not drawing this real accurate, but something like that. So what kind of discontinuity is this? Removable. And we can pick that out because my conditions are equal and not equal. So it's discontinuous at negative 2, and that is removable. All right. Take a second and look at 9 and 10 and see if you can identify. Correct. And then you see that the x cancels. Okay, so there are two discontinuities here. Anything that makes the bottom 0. So for this one, that would be x equals 0. This one would be x equals negative 3. You have to classify each of those. So at 0, if it cancels, what does that mean on the graph? It puts a hole on the graph if things cancel. And that, when you have just the hole on the graph, that is removable. If it doesn't cancel, what does that mean we have on our graph? Vertical asymptote, so that means it is infinite. So 0 is removable and negative 3 is infinite. Number 10, nothing factors there, so we can just jump straight to it. It's discontinuous at, the only thing that makes the bottom 0 is 1. Since that doesn't cancel, we know we have a vertical asymptote, so that means it is infinite. Okay, we are not done. I know I've talked the majority of the hour today. I apologize, but sometimes that happens. Tomorrow we'll finish up the notes and we'll also do the back of this handout together. I am going to go ahead and give you the homework for this section, and so it won't be due until Thursday, but it's going to look very, very familiar. Same setup as the handout we've been doing together in class. So you could probably do a large chunk of it already if you choose to. What is today's Wednesday? Yes. So how about Friday? Yeah, not due tomorrow, it's just Thursday.